Good evening. On behalf of Engineers Australia, I'm delighted to welcome you all to our Infrastructure Thought Leaders series on retaining walls. My name is Amanda Rogers and I will be your host for tonight. Firstly, in keeping with our tradition, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. In tonight's webinar, our speakers will discuss how the continuing boom in the building sector is influencing the design and construction of retaining wall systems and how we can keep up with current as well as future demand. Our speakers will provide insights and share case studies on structures referencing real-world examples. Before we get started, I'd like to acknowledge that tonight's seminar is being hosted with our long-standing industry partner, Austral Precast. Austral Precast is a leading provider of high-quality and innovative customisable precast concrete product solutions. Operating from plants located across Australia using state-of-the-art technology, production techniques and systems, Austral Precast provides a diverse range of customised products and specific precast solutions. Austral Precast services a range of markets including multi-residential, commercial, industrial, community and civil sectors. I'd now like to welcome our first speaker, Kim Guttridge. Kim is a senior civil and structural engineer with more than 30 years experience in design and construction in commercial, transport and infrastructure sectors in Australia, Hong Kong and Southeast Asia. Kim has a wide breadth of experience from infrastructure to architectural structures with recent project accomplishments in Melbourne's transport network and underground structures. These include Springvale Road grade separation, Caulfield to Dandenong elevated rail and Melbourne Metro. This experience has provided Kim with a complete understanding of multidisciplinary design and can effectively work in a key design manager role and a structural lead role. Please join me in welcoming Kim Guttridge.
Thanks, Amanda. Last year, Engineers Australia presented How Retaining Walls Fail with Dr. Chris Haberfield. He covered the principles of retaining wall design and construction in a detailed manner, with failure and risk highlighted. It does seem to go hand in hand with retaining structures. However, this talk is mainly focused on details from large infrastructure projects where the design life and the importance of the retaining wall is high. If you're an engineer relatively new to these structures, this talk provides current project context to the terms and principles that are key in today's practice. For those with experience, you may need to follow up later on what is presented. One could spend hours on each principle I'm trying to cover here in the slideshow. I'll first look at embankment retention with fill behind the wall above natural ground. Here we have soldier pile cantilever post and panel walls. These are very popular at the moment, and I'm sure that you'll be designing one of these if you're in the industry. They're definitely trending. They're economical and space efficient and fast to build. Post and piles are spaced in proportion to limit plank size to a minimum, along with ensuring the passive resistance of the ground in front of the pile is not overstressed. We do that by spacing the piles at 3 times their diameter as a starting point to the design, and we balance the active and passive forces according to the advised soil strength. There's some theory later that I'll cover that off. Sometimes smaller walls are designed without ground information, which may be appropriate for low-risk walls. Low risk is defined in AS 4678, Earth Retaining Structures Code. Using upper bound loads, lower bound ground strengths with geotechnically approval of the ground while it's open might be a strategy. This will probably mitigate your risks, but in the end, I think we'll be too conservative. So note the difference in this post and panel wall, where you can see that earth and air and water is in contact with the structure at the front and at the back. To me, this is indicative of a lower design life than we're used to in the large infrastructure projects that I'm featuring in this talk. So the next slide here, it's showing you the Caulfield to Dandenong project, where we had 4 kilometres of post and panel, embankment, some of which was retained with post and panel systems. It's very similar to the previous slide. It has a more, but this actually, you can see that it's retaining a train embankment. So this automatically gets a more important criteria, and therefore we are designing to a 100-year design life. So to cover off some of those features, you notice the difference in the front of the wall. We're controlling the water and ponding and the splash zone. And we're providing a corrosion allowance on these posts, which are much thicker than the previous ones. And behind, we've also got good drainage. We tend to use AS 5100 for these 100-year design life structures in the public realm. So the Earth Retaining Structures Code allows a 1.25 factor for multiplying earth pressures to increase your earth pressure distribution, whereas recognizing the longer life and the higher probability of a higher load, AS 5100 ensures that you multiply that load by 1.5, so a bit of a difference there. Next slide, we have the same project, Caulfield to Dandenong, where this is a lesser important wall, where we may have designed this with a lower importance factor, and you can see that it has a garden bed in front, and it's not retaining the rail embankment. So it's still has a corrosion allowance, I would say, and attention to detail in drainage. In the Caulfield to Dandenong project, we have panelized retaining walls, which are popular in the scene at the moment. I'll just find it down here. We adapted the what's on the market at the moment for panelized strapped retaining walls to a tension tie. This was a great innovation for sustainability, as Site 1 spoil, which was contaminated, could be used as the fill, which would be very expensive to dump elsewhere. So the tension ties attached from this side of the wall and are resisted by the other side of the wall. There's many construction stages, but it still stacks up economically. There's this clamping and the management of the tape to prevent material falling through the strip drains, and propping to the safety code of the day. And you notice that we also lay back the wall at an angle that's around 1 in 40. So it reduces the impact of the wall when you're standing in close proximity to it. So don't forget, this is the public realm here. And so it is a piece of architecture. Laying back the wall also allows, for displacement to occur, because the tension system requires a bit of displacement to take up that load. Here's the next slide shows that the tension ties here, and the piece of equipment that allows this to occur with fixed connections into each panel and running across the earth fill. It's important to note that we are observing the 100-year design life with enhanced durability on the straps and the knuckle. This is a bitumen wrap around, and I think all the elements are also galvanized. So bear with me while I get this information here. So with retained embankments, if you really want to fully realize the savings to the infrastructure costs, we need to perform as little subgrade improvement and excavation as possible. So then it's like placing a surcharge on the natural ground of around 200 kPa. With train track settlement criteria, we have to be very sure that of our short-term, long-term settlement performance of this. And so definitely this is a domain of the experienced geotechnical engineer, and their weapon of choice is the finite element model, which this is a graphical depiction of the model. And so you can see that we have existing tracks beside, which also would be limited to any displacement. So this is just to depict how global stability is very important when you're designing these walls, and it'd be quickly the economics would definitely switch around if you were to provide too much foundation below here. So therefore, a lot of analysis to confirm that putting this on the natural ground is not going to settle too much. Now, moving on from here, I'm going to go into excavated walls, or walls below ground, but just to finish off the modular panelized retaining systems, the precast L, the gravity wall, the classic gravity wall, we used quite a bit of on Caulfield Dandenong project, and is still a very economical way of construction where the natural ground is strong and there isn't too much surcharge. I'll show you in a minute. But onto, I'll show you in the theory. Onto excavated walls. This is the Springvale Road grade separation. With the state government's push on grade separation removal, I think every retaining structure known to man has been constructed in this city of recent times. But last year, Chris mentioned in Why Walls Fail talk, he mentioned that a wall of this type carries a whole lot more risk in design and construction due to the unknown conditions of the natural ground, whereas the above ground ones are filled to engineers' specifications. Anyway, this wall features on the left 900 millimeter diameter soldier piles at 3 meter spacings, and it's constructed by the CFA method. We're temporarily propping the wall at the top, and the props are removed once the base slab is cast. So that's a medium-sized excavation up to around the 10-meter mark. I would tend to call them a medium size, where you may or may not have props. On the right, there's a 900 diameter seek and pile wall. It's the same job, just a little deeper in the excavation, but also it's retaining quite a bit of water, groundwater, at the level where you see the bulbs of concrete coming out. That is the CFA method, not enjoying that change of stiffness in the ground. And so that wall is over 10 metres, and it required permanent props, as you can see at the top. Moving on to bigger walls. Sorry, just catching up down here. Deeper excavations greater than 12 metres with requires multiple levels of strutting. This excavation is over 20 metres deep and is being retained by a 1 metre thick diaphragm wall. You can see in the foreground there. Compared to all the structures that we've shown now, this is significantly larger structure. The main drivers for this ground is the groundwater, and you can see heavy construction vehicles surcharge on the side of the wall, and strict movement limits required, so tight deflection of the wall. So these walls require sophisticated multi-stage analysis. I can show you a bit of what we do there for safe construction. So multi-stage FEM analysis looks a bit like this. We have 3 levels of strutting. I note that, sorry, move the slide on. We have 3 levels of strutting. Diaphragm walls on the outside, the stratigraphy in the ground modelled, and the horizontal blue line are the slabs. So this is a construction stage well down the analysis pathway to the final stage where the slabs have been modelled. The soil structure interaction models the relative stiffness between all those elements in different colours, and every step of construction is modelled and force and displacement envelopes produced. So that's how we do those deeper ones. Moving on to something more sophisticated is three-dimensional modelling on the right. So if you want to capture those forces, corners and stiffening effects in the other direction, you can with three-dimensional modelling. The capture on the left is a very important step for structural engineers and geotech engineers to document the controls to the builder in their design set. So labelling soil levels, water levels are very important to label, propping levels, assumed loads, and anything else that you can think of. So it's very important to capture that and put all your assumptions down. And when you get very good at it, you could possibly do something like this, which is this is the Queen Victoria Hospital in Lonsdale Street, which was quite a while ago now, 15 years ago perhaps. I was very impressed with, and probably spurred me on in my career. So this is an island of stressed anchors through the retention wall. So they are piles and panels that have anchors which are actively stressed, or they're known as active anchors, to try and mimic the original confinement or the in situ stress state of the ground as not to disturb the heritage building sitting on top. Fairly economical to build, especially when you have a broad site like this, so where propping is definitely inefficient. Temporary propping. You can see that the floors there are going in, and once they're built, those anchors can be de-stressed. Often, though, on sites where the anchors tend to be long, they tend to be, at least as long as the height of the wall, and where that extends beyond the boundary or into poor ground, that you can't use that solution. All right, into a bit of theory. Just quickly, this is the the gravity L-shaped wall that I was talking about, some of the terms that structural engineers need to have under their belt is the Ka, K0, and Kp. So Ka is the active earth pressure coefficient, and Kp is the passive earth pressure coefficient. Ka is associated with the least sort of earth pressure forces. So here's the sloping line. There is the pressure diagram, pressure distribution that is what you taught at university, I'm sure. So the benefit of the precast L is very simple to precast. It is trending in modern parlance at the moment. Architectural finishes on the front, maybe up to 4 meters high with low surcharge at the back. Surcharge is the same as live load. So these walls tend to fit into that category. The problem we had on Caulfield to Dandenong was that once we put them with a high surcharge, we had to use at least 10 or 20 kPa at the back. And if we plonked that at the virtual plane, as shown there, we generally got a sliding issue. So they weren't the best after that sort of proportion. So Ka requires the wall to move to develop that low pressure. Next is the some Kp demonstration here. The passive resistance. It's so it's an embedded wall. It's not into a rock socket. It's into some ground. It's the largest of the earth pressure distributions, and you can see how the wall, being very stiff, is deflecting outwards in a single curvature, and therefore producing the bending moment diagram you see as classic, just on one side, tension on one side, and you can clearly see the failure mechanism there is toe rotation. So if we introduce a stiffer structure again and prop it, we end up with this situation. And I've also introduced compacted ground behind here. So it usually gets compacted in layers, and that can produce a artificially high locked-in stress, which, by the way, if you refer to AS4678 in Appendix J, you'll find a good approximation for that load. So you can start to think about the soil structure interaction with this arrangement. You're thinking Kp influence pressures and K0. It's not moving, it's not allowing Ka to develop, and therefore you can predict the deflected shape diagram, which I'm sort of exaggerating at the bottom there, but I'm expecting the bending moment diagram to cross from one side to the other, and the shear force and bending moment diagram crossing. If you were to add a surcharge, again, I'm exaggerating this. This is probably the most accurate. In my mind, the Boussinesq distribution is the most accurate representation of that. And in the end, if you follow the thick black line, notwithstanding this Boussinesq is exaggerated, you can envelope the design forces. So, should you employ finite element and some modern methods, which we always do, using the embedded wall example here, you can see you can see how the computer does it more accurately, or the model does it more accurately. the geotech engineer required to choose the inputs. He chooses soil parameters and the stiffness of the stratigraphy, any water, and then assigns the initial stressed state, K0, to the model, and then the construction activities from there on will produce KA, KP actions. And so in for this particular construction stage, you can see the green lines at the back is the active earth pressure that's developed, and you can see that the model has a limiting number, which the geotech engineer doesn't want to go less than that, and the limiting value for KP doesn't want to go more than that. But this actual construction stage is developing these sort of pressures, and when you arrive at an envelope, you can envelope it that way and reinforce accordingly. It's important to note that the FEM will determine much more accurate soil deformations, and often the structural engineer then requests a rerun after this initial run in accordance with any structural limitations he or she might have on the structure. And so then it's an iterative process which will lead to a much safer, refined result. What is necessary in our work is monitoring when we do retaining walls. Any retaining wall, all retaining walls, refer to the Earth Retaining Structures Code. There is a section on monitoring. This is during construction, but also in service, there's a recommendation to inspect and ensure that that structure is travelling okay. This is deep excavation, and what we've monitoring here is the force in those orange props, which is a good, it is measuring what we predicted in our models, and it's very good to follow up on this sort of information. So day one on the left, and the blue is the raw data, and the orange is corrected for temperature. So my red line there is plotting hot days and the prop expanding, and colder days. And we put our prediction on there, and we must have a path for action predetermined when things don't go quite right. So here's a processed. The previous slide was raw data. This is processed data, and so you can see that you can explain the rises and the dips, and when you start to exceed the predictions in your model, then there needs to be absolute stop work and some action in between. So that's for the project team to determine. So last slide, I'd like to leave you with these are the references that guided me through my work with retaining walls. I'm not going to talk to them, but you might want to take a note. And so thank you for your attention.
Thank you, Kim, for your presentation and insights. I'd now like to welcome our final speaker, Dr. Jim Yang. Jim is Arcadis' Senior Technical Director and Regional Technical Director of Geotechnics and Tunnelling for the Australian region, with responsibilities that include team leadership and the technical delivery of all major projects. Since joining Arcadis, Tim has built the geotechnical and tunnelling team into a group that can provide full geotechnical and specialist tunnelling services, from site investigation through to detailed design. Jim is a chartered professional engineer with over 25 years of experience in leadership, management and design of infrastructure and building structures within Australia and also overseas. Jim has published over 60 technical papers and invited lectures. Jim was the co-chairman for the China Tunnel and Bridge Summit in 2012, 2016 and 2018. Please join me in welcoming Dr. Jim Yang.
Thank you, Amanda, for your nice introduction. I'm going to talk about design and construction considerations of seawalls. The outline of my presentation, first of all, I'm going to talk about different types of seawalls, design consideration of seawall and log consideration, and how their combinations should be considered. Some of design challenges we experienced from one of the project cases, and in the end, going to wrap up with some takeaways. It's interesting to look at what's the definition of retaining wall. There are two main parts. One is retaining wall always used to look after the level differences, and that's why we need to have a structure. However, when one side is the sea or water, and the other side is on land, and then we call seawall. And depends on the material we use. We can form different of retaining revetment or retaining wall or protection walls and so on. But one of the applications we use is to use precast elements to form interlocking blocks to protect, to form a seawall or revetment. What are the considerations as compared to normal retaining wall to the seawalls? Seawalls, we usually need to consider not only the earth pressure, live loads, wave loading, and sometimes tsunami effects, earthquake loading. And it really depends on the materials we use for the seawalls. Can be precast or cast in situ or steel or concrete. But in terms of design, we need to consider both ultimate and the service conditions, and to check the sliding, bearing, and overturning of the entire wall system. And sometimes we need to consider what are the construction, compaction, or vibro compaction adjacent to a structure. And I'm going to talk about a case study of Port Botany expansion project, which completed more than 10 years ago. The client is Sydney Port Corporation. The advisor to client was AECOM, and the builder was Borderstone and Yandano. Arcadis was the principal designer, together with Scott Wilson, and the Goddard was the Geotech, and WSP was the project verifier. First of all, let's look at what's happening in the Port Botany area. It experienced a long history. At the very beginning, the Sydney Airport was constructed through reclamation works, and the first runway was completed in 1975. Then Port Botany work started happening, and by about 1984, the port facility completed. And then in about another 10 years, the Sydney third runway completed. And the last slide shown there, around 2008, actually this is a Port Botany expansion work is happening between the third runway and the existing Branson's Dock area. You can see there. So the scope of work of the project, PBE project, is to complete a northeast berth, east-west berth, and a tuck berth there, and the revetment works there, and a bridge access to the new claimed container yard there. But this contract primarily is the civil works. Because the original Branston Dock was constructed using counterfoot system. So the first option we look at is the precast counterfoot system. And this is showing basically a series of counterfoot stitched together through a curbing beam. And that's the precast yard there. And this showing how each of the counterfoot is placed into the sea. In this picture, showing a person compared to the height, which is 20 meters, and to demonstrate the shear volume of each counterflow unit weighs 640 tons. The main requirement for PBE project, certainly we need to consider design vessels, the ballast system, and the containers behind the wharf, and also the operating crane to lift and moving the containers. One of the particular requirements for the seawall is to achieve 100-year design life, because the entire area is to be backfilled using reclaimed fill. So long-term settlement of 250 millimeters at 20 years. The wall itself, vertically, horizontally, cannot be more than 40 millimeters in 20 years. And at the crane gauges, the differential between the two cannot be more than 30 millimeters. And there are numerous other requirements at different time of the project site. And also, we need to satisfy the seawall global stability against sliding, bearing, global stability, both for circular and non-circular, under the sustainable load case and also operational load case, plus the earthquake conditions. All the factors if this summarized there. So the ground condition as a geotech. So we're looking into the ground condition, and there is one layer, this unit 3 here, is of great challenge because it got fissure clay, which was discovered during construction of Brazil Dock. It has very low shear strength. However, it will be the founding material for the proposed counterfort. So that's one of the challenges we have to consider. What's the gradient level we need to consider? And for the counterfort itself, what is the earth pressure? Ka, K0, or a K somewhere in between? How we can take account of the variable compaction induced load on the counterfort? And what is the virtual back condition? Should we consider the vertical friction as K, same as normal friction, or 2/3 of it? What is the earthquake condition we should look at? Because there are 216 counterfort units there, so the optimization of the structural analysis has significant implications on the total cost of the project. Further to that, there are corner blocks at northeast corner, northwest corner, and also there is a transition between existing to the east-west berth. And after assessment and evaluation, and this is the typical cross-section we developed. So the counterfort itself is about 20 meters in height, 9 meters into the page, which is the width, and the width across there is about 50 meters. The finish level of the pavement is at IR4, and then the trench has to be dredged down about IR -30 and replaced by reclaimed fill, plus the variable compaction. And then we use a gravel layer there before placement of counterfort as a bedding to ensure the bearing capacity will be adequate. The load cases we consider, there are two main load cases. One is the sustained load case, as shown there, and this one is the transit, where when the ships are docked there, and plus the earthquake conditions. For the earthquake, we look at the various return period for one of the, because it's a 100-year design, so we look at a 1 in 1,000 return period for stability checks and deformation assessment as well. The typical process for the counterfeit unit assessment, I was using a Plexus to look at the earth pressure developed behind the unit, and then using that as an input into Plexus Strain 7 3D FEM structural model. After a number of iterations, until we get similar diffraction output, then we can stop. Otherwise, we have to continue the repetition. Once we achieve that, and that earth pressure is considered to be the reasonable earth pressure behind the wall. So design outcome is there. The red is the K condition, and the green is the K no condition. So the black is the recommended earth pressure profile. So somewhere in between, at the upper part is close to the, more or less close to K condition, and the lower part is very close to K no condition. Because this structure has to be designed for 100-year design life and in an aggressive sea water environment, the crack width control was one of the critical considerations, and the reinforcement in the control unit was very much governed by the crack width control. And after we used this iterative approach, it was found that the design team and contractor building up the confidence, put the right reinforcement in the right place. So this is showing the corner blocks I mentioned earlier. This is the northwest corner. In the corner itself, we use actually a blockworks, both shown there, and the ground anchors to tie them together. Further to that, the curbing beam was much wider in the corner and gradually transitioned to the standard width, so that to avoid differential and rotational movements. Similarly, for the transition from the existing to the new east-west wall, also got much wider curbing beam together with the blockworks plus the infill unit put in there. And at that time, we also actually did a Plexus 3D modeling to evaluate what would be the differential movement and the rotational moment at the curbing beam level at the corner blocks. So we modeled the northeast and the tuck burst for this case to assess the moments, and also it was found that the arching effect actually does contribute to the earth pressure development behind the wall. And the results actually was very similar to Plexus 2D, but certainly at that time, because the limitation of numerical capability, we cannot model the variable compaction effects on the counterfeit itself. After the wall is formed, so we need to look at the global stability and to determine if the dredging level was sufficient to achieve the global stability. This is showing a non-circular failure. We need to target to achieve a factor safety of 1.4. This was interesting that this was actually agreed by Singapore after negotiation at the tender stage and the post-tender process. So this slide showing the construction sequencing in general. So we're dredging to about minus 17 and then form a trench and to get rid of the fissure clay. Then we put back at the reclaimed sands, the yellow showing variable compaction, and the width actually overburden to about minus 13.5. Then we trim back, put a gravel on, put the unit on, and then after the wall finished, we put a reclaimed fill to about 2.5 CED. Then we did a fiber compaction again behind the wall. After that, one particular thing we did was put a cantilever about 300 kilonewton per meter above the contour for 3 days, and 90 kPa surcharge actually behind the wall for a month to minimize the differential segment. Then after that, we remove the surcharge, then we build a curbing beam and the remainder of the field. And this is picture showing the fiber compaction process. And this slide showing step by step how this massive conical unit was lowered into the sea. And of course, you require a very large barge to lift it and move it to the right place. But one would wonder how these units were connected. And a couple of things. The first thing is there is a physical gap when the units are placed. Then there is a flexible membrane actually between the two units, so it will block all the potential loss of the sandy material behind it. Then we have a notches there to put a grout backs to ensure that it'll provide the strength as well. And then we have a curbing beam which will stitch the units together, acting as a wall. So as part of the reclaiming works, fiber compaction QA testing was very important. So first of all, we actually established a site to try, and using a CPT profiles before and post fiber compaction to optimize the grid pattern. What's the spacing, and then also to verify the compaction index of the sands, and to determine what's the right equipment to use for fiber compaction works. And this is showing a tri pattern, different grid spacing, and also look at the different level energy. So full energy, and also look at the reduced energy, because we're close to the wall. We don't want to push the wall too hard. Then it will induce lateral movement, and we're trying to avoid. And this, we actually put the lower cells behind the walls, and to check, during the fiber compaction, what are the stress level increase. As you can see, actually almost double than the sort of earth pressure during that process, and then but it will be less than the structural capacity. So because it's a transient low, and only lasts for a few seconds essentially at that particular location. And what we have found is the post fiber compaction earth pressure is quite close to the original, which implies places predictions, and that gives us the confidence that to finalize the fiber compaction and the patterns and the equipment. Then for the one very close to the wall, we actually use the reduced energy to ensure the wall is not going to push out towards the sea too much. And of course, like any geotech or earthwork projects, and instrumentation monitoring is the key to success. And there were more than 1,000 monitoring points there, and the main elements to check was the movement of the structures, conical, curbing beam, and so on, and also the earth pressure developed behind the structure and the anchor loads. And we adopted the traffic system together with the mitigation measures if the trigger values are exceeded. And this is a typical monitoring result. We spoke about the pressure increase during variable compaction, and this is the monitored settlement at a challenge 550. You can see the wall movement is very close to the prediction, slightly less, a little bit, at one point is a little bit more, but overall the settlement is a bit of less. I think that largely due to the preload or surcharge we applied. And there are a few more construction stage photos. So this is where the precast yard was established first after reclamation, and as construction progresses, the reclaiming area getting bigger, and more counterfort actually has been formed, and this one is getting closer, and this one pretty much showing the complete one. And this shot I just got from Google is it's almost finished, and this is the sort of finished product of the wall. And the after the civil works finished, you can see the pavements of the container yard being constructed, and other associated work also being carried out. And Arcadis is as of today continue to involve in the project works. And I just want to recap, what are the key things that in the design of these massive sea walls. So innovation to the code of practice. It's very important to use the state-of-art analytical tools to assess and building up the confidence in design. And this project basically has shown that precast technique is very powerful to save time and money when you're building up these massive retaining walls, and also actually to enhance the quality of concrete, because your precast, what's happening, to ensure the durability aspects of the concrete structures. And in terms of the dredging levels, the integrated design and the constructability assessment, because we decided to go -30, which is really important because we can decide the most economic dredging tools, and we don't have to we also save the volumes for reclamation and trench backfill. And the sort of varied profile of the earth pressure between KA, KNO also that achieve the savings of the comfort unit. And as always, in the geotech and earthworks, instrumentation monitoring give us the real-time feedback to ensure that if something gone wrong, we can take the mitigation measures, and hence to make sure the project will be successful. I just need to really thank all the team members who contribute to this project. I myself only did a fair bit of tender work, but peer reviewing lots of stuff, so during detailed design and construction.
Thank you, and welcome back. Thank you, Kim and Jim, for two fantastic presentations. Our speakers will now come together to take questions from our audience. Thank you for those that sent questions in on registration. We've got about 25-30 minutes to go through them. We've got lots of questions, so make sure you send your questions through for the panel via the chat box on the screen, ensuring you provide your name and who the question is directed to. Thank you. We'll give Jim a rest and kick off with Kim. We've had a question from George in the US, who is asking, what are the main considerations to be considered for drainage systems on retaining walls? Kim.
Right. I hope you can hear me okay. Thanks, Joel. I think that considering the maintenance of that system, it's very easy to install something. It's difficult to install a system that will be maintained over the journey, but also making sure there is a very achievable pathway of water out of that retaining wall. Yeah, it's a broad topic and a very important one. So, sorry, Jorg, I could probably talk quite a bit longer on that, but yeah, it is worth spending a lot of time on the retaining wall draining system.
Thank you. And Kim, just don't go anywhere. We've had a question from Sam Woon, who's asking, in terms of underground water pressure, where can you discharge the water? Over to you, Kim.
Well, I think is alluding to drained, undrained, deep excavation situation. So the tendency these days is not to drain structures, but if we do, then it's under the condition that it's a trickle, and that we drain it to a stormwater system, or we have a separate system, but it is not a significant flow. You can't drain the neighbourhood, so it's under those conditions only. Jim might have another thought on that.
Jim,
Not sure if that answers the question.
Yeah, I think it's a very interesting question that, in general, depends on your size situation. For example, I'm based in Sydney. Lots of deep excavation basements are like a drain in a way, so that the water, you're always going to have some water. Basically, you're going to collect it, but they are like a DA conditions. You have to treat it these days before you discharge it to stormwater system. That's essentially most of the basement in Sydney are drained. Unless you circulate to the sea, then you have to have a like undrained situation.
Thanks, Jim. Thank you for that. And we've had an interesting question that's coming from Rod, and Rod's viewing from New South Wales on recycled. What recycled materials are being used in the design and construction of retaining wall systems? Great question, Rod.
We've used backfill from if you recycle material that's suitable for putting behind the wall, that's a good use of spoil or product. For the facing, for the concrete, I think there's not too much in recycled material that can go into that, because we're designing to high loads and high performance. So yeah, nothing further to add on that one, I think.
Jim, do you have any thoughts on recycling?
Yeah, I think it's a very good question. I mean, especially the international trend now, sustainability is one of the very hot topics. It's almost actually in very large DNC project, for example, the government is promoting reuse of material, and recycling certainly it's very important aspects for consideration in our design development. Now, I have personally sort of experienced some recycled material, for instance, the use of a lightweight fuel, for example, for one of the jobs that we did involved last year. Especially when we build an embankment on a soft ground, we're trying to reduce the weight of the fuel, for example. And also in the pavement space, I'm aware of that. It's not necessarily retaining wall, sorry about that, but certainly recycled material has gaining I use the word gaining momentum for different applications. So certainly there was a durability concern on certain side of it, but I suppose it has been encouraged to consider more and more recycled material.
Yeah. And that's good to hear, because I know we set this topic in, with the current building boom, the whole environmental and sustainability is an important factor. Bradley in New South Wales sort of thrown the discussion out quite broadly, and a few people have come grouping this question, but using Bradley's, he's asking, and Jim, maybe we'll start with you. What are the main differences between commercial versus residential retaining walls that we need to be aware of?
Yeah, I think, well, when we're talking about residential, I mean, lots of people probably doing DIY stuff, if you got a meter or half a meter, you dig in your backyard and building up other brick or block works, you kind of doing something by yourself. That when you look at the risks, for example, that probably relatively low risk because the wall height is not very significant. Now, if you go to engineer to prove that design, and probably he's not going to put his signature against it. There's lots of things like the drainage. One person mentioned from US, Kim talked about that. It's very important. You got to take that into account. But for the commercial ones, for anything, I mean, first thing is that any commercial product that in general you would have a recommended practice, i.e. there will be a kind of design guide for you to consider. Certainly, you need to consider some basic stuff and different type of wall, whether it's a tarback wall or gravity wall and so on. So I think I kind of can see there is a fundamental difference between the two that hopefully addresses your question. I don't know whether that's what you're thinking about in your mind when you raise the question.
Kim, do you want to add to that at all?
I'll probably only add that start at AS 4678, the Earth Retaining Structures Code, and ask yourself about the importance of that wall, and then follow the design pathway from the importance, and then you'll be factoring using bigger factors if you're concerned about certain things, or lower factors that the code allows if it's low risk. But yeah, any wall, if you don't address the water, you'll be in trouble.
Thanks, Kim, and thanks, Jim. Great questions come in from Siddhartha in Victoria, talking about sand dunes, asking what consideration should be taken when working in sand dunes. Jim, do you want to kick off on that one?
Yeah, well, first thing I do acknowledge that I actually do not understand the context. That is it talking about the sand characterization itself? I mean, the case study I presented was about a seawall actually and using reclaim the same material. So it's a massive, like 20 meter plus retaining structure with sands all behind it. So from a mechanic point of view, the sands is the best material to use if you're doing a retaining wall. Now, I'm not sure whether the person that raised the question is talking about some sort of natural instability or it's moving problem with wing or anything. I just don't know. But in terms of retaining wall design, in terms of mechanics, I think sands are one of the best materials you can get.
Thank you for that. We've had a great question based on this event when we talked about innovation in our synopsis, and Joseph, who's also in Victoria, has asked, and Kim, maybe we can start with you. What are the latest economical and innovative solutions available in retaining wall systems? A very important question.
Yeah, I think the strapping and the tied walls have come a long way and are very with the sophistication of precasting now. There is some very creative walls going on. So I think there's been a lot of innovation in that space. The precasting also, as I mentioned in my talk, that also leads into the gravity walls in certain circumstances, strong ground, and if you need a rapid build, then precasting an L shape and putting it on the ground is a good solution. And one could call that an innovation because years ago precasting wasn't, and transporting precast wasn't as good as it is now. Jim?
Thank you. Jim, do you want to talk about innovation in retaining wall systems?
Yeah, I think if you look at the kind of, I mean, in any, or first thing I would say that in civil engineering, the I call progression rather than innovation actually, because the construction, the new material come to the market, it's much slower than the IT industry, for example. So and there is another fundamental roadblock issue here. For instance, the government actually probably I don't know. I got to be careful what word I should use here because it depends on the audience. But not sometimes not encouraging the innovation. So the government set out a lot of guidelines for retaining system design, and for instance, if especially for the mediation work, for example, we're trying to do something like a relatively innovation or different from the standard, then it's nearly impossible because of the timeline required to get approval from the authority. And so I suppose one thing that I would suggest is that sometimes the authority need to be more open to encourage actually innovation, so then we can introduce more like new products to the system. So and of course we, as a designer, whoever that will be, need to assess what's the consequences or assess the risks will be for new products. For instance, you need to have a closer monitoring, for example, check it out in the long-term life.
Thanks, Jim. From innovation to standards, we've had a great question from Adam, who's in New South Wales, asking what is the code standard for determining earthquake loading for retaining walls? I'll throw that one open. Who wants to pick it up?
I have just sort of been thinking about that, Adam. The AS 1170.4, is it the loading code for earthquakes, needs to be referred to, and then AS 4678 Earth Retaining Structures Code has a method that is good. It's a good code. It's got full of handy information. AS 5100, though, will have to be used for structures that have a longer design life, and so you need to cover more events, and you need to think about more important. If it is an important structure, then you need to switch to AS 5100 instead of 4678. But always refer to Earth Retaining Structures Code. The methodology in there is good.
Thanks, Kim. Thanks, Kim. And as we've been talking about innovation, and you referenced, Kim, Chris Haberfield and his failures presentation. Andre, who's in Africa, is asking, and we've had a few questions around the failures. What are the most common failure modes of retaining walls if not designed properly? That's probably another webinar for us to do. Jim, do you want to start with that one? Well, maybe Kim, because you referenced it.
Just movement and
Kim, you go first.
Yeah, it's just, what do you call a failure if it moves too much? We've all seen catastrophic failures on the internet for where unfortunately loss of life has followed. That to me is invariably the lack of management of water or under design. So there's that. But I think in the more common construction, it is probably a lack of understanding of soil and its behaviour. And yeah, your wall will probably move too much.
Thanks. Jim, failures. Obviously, part of the retaining wall.
Yes, last year, it's in a similar series. Actually, I spoke about a number of case studies that I personally involved on you know, I always got to be very careful when you use, failure, because, the mode of failure actually depends on the importance of the structure and the consequence of the structure you actually design for. So that's probably is something to, for anyone that design something, got to keep that in mind, because what is your design criteria, and what is the definition of a failure? For example, Kim mentioned something early in his presentation. For certain retaining structures, actually, because you got rough, say, railway behind, or train load behind, or important highway behind, then when you design a retaining wall, the deformation can be very important. Therefore, your retention system, that when you design, it's not only the ultimate limit states, i.e. the factor safety you need to achieve, but at the same time that you need to check the serviceability limit state. So this is actually two fundamental requirements set out in any of these ultimate limit state codes these days. So that's probably one thing to remember when you design. Then when we talk about, say, okay, well, if the wall basically collapsed, that somebody killed, so that sort of consequence, I mean, it's very, very severe, because you can't kind of go back and restore it. However, but if the wall moved a bit more than normal, now I think I did last year's presentation. So actually, you still can use part of the wall by strengthening, the I could over move the wall, and the part of the wall still can be used by restoring, for example.
Thanks, Jim. Had a great question from High New South Wales, who's asking, looking at from all your experience, everything you've done, he's used the word, what are some of the most challenging designs? Maybe we'll also say the exciting designs from a technical, contractual and compliance aspects that you've done or been involved in. Kim, how about we start with you?
The rail space would definitely top the list for me, in that the number of approvals and stakeholders and constraints that one has to consider, and all the other disciplines that are feeding into that design have an approvals process that goes through several steps, and in the rail industry is tightly controlled. So any one step can change your structural design or your geotechnical design. So that is the most challenging, without a doubt. So the other, I suppose, a deep excavation presents the most engineering and modelling challenges. One has to have many load cases, many considerations of what can happen in 100 years, and the model can be a whole city block, perhaps. So that's the short answer. Happy to drill down a bit more if you have a specific question.
Jim, do you want to talk about some of the most challenging and / exciting projects you've worked on?
I I think given so many years of experience, but it's a kind of quite difficult to single out a one. But certainly the one I just presented, as an individual engineer, I think it's a lifetime experience like this pole botany precast unit and 20 meter plus seawall. I don't think I'm going to work with another project of this scale, for example. So I think it's a kind of I feel proud of it. I got involved in that job, and that's why I share a bit of history of this sort of side how it evolved along. But that's one thing. And the other thing is Kim already mentioned, I mean, Kim and I work together, for example, like a maybe metro, for example, you got excavation as deep as about 36 meters, for some shafts, and you got buildings next to those bigger holes. And part of it, you see, I always, when I talk to structure and no offense, when you're doing a building, just 36 meters above, it's very tall. But when we're doing something depressed below the ground, nobody can see after you've done the work. So kind of, it's very different sort of work we do when doing underground retaining systems. So I suppose certainly when we deal with sort of natural formation of soil or weak rock defects and so on, it's a lot more challenging than you're building up a retaining wall that you can see that it is above ground. So.
Thank you, Jim. Thank you for that. We've had a question from Nicole in New South Wales. It's a question that she's actually phrased it, but can keystone walls still be constructed in Australia? Which I think the answer is yes. But Jim, would you like to talk a little bit about keystone?
Well, first of all, I admit that I actually haven't done a lot of that sort of type of walls, but I only look at some of the kind of brochure or some. But the principle is very similar to any block kind of wall. It can actually do tie back, and these priority sort of systems, I think it has their own kind of speciality, and whoever that get involved in that sort of wall design, you need to first of all understand, how that system works as an engineer before you do something or draw up a block on a piece of paper. Then, because you are the one that if you do it, you're going to be responsible.
Thanks, Jim. This is a very specific question, Kim. I think it's come from looking at your presentation. But Yash is asking, what are the red steel section used on the diagram of 1 meter thick retaining wall? Is that?
Well, they're called struts and whalers, and they're temporary props to excavate down. So they're massive. What were they? They were about 1 meter deep, and I hope I'm answering the question. 1 meter deep, and they were paired because they're a strut, and struts are inefficient when they try to buckle. So we put two together and bolt them up, and they have a much higher capacity. So it was a proprietary system. That one, actually, someone in Singapore, a company in Singapore, had come up with a bolted system that they could reuse and recycle. I hope that answers the question.
Thanks, Kim. And just staying with you and your presentation, a question's been asked is how deep are the anchor bars that were installed on the wall of the Shot Creek base?
I presume you're talking about that island of ground with the hospital on top, the old heritage building. If they would be well, some of those would pop out the other side, so they're 20 to 30 meters long. Deep, I'm not sure about deep. They go in at an angle more horizontal than vertical. There are no other anchor bars, I believe, in my talk. I think that's.
Sorry, it's a bit difficult.
They were cables. They're stressed anchors, so they're not actually bars. Yeah.
Thanks, Kim.
I think
that's great. Sam has come in with it. We're drawing to a close, but we do have a question around soil corrosion. And Sam is asking, what methods are there to avoid soil corrosion and overturning the retaining wall? Jim, do you want to discuss that a little bit?
Yeah, sure. So that two parts of the question. One is that the soil aggressiveness certainly, as a good practice that and the Australian current code practice do encourage you to do the site investigation, and one aspect of the site investigation is to do the sampling and testing of both soil aggressiveness and groundwater aggressiveness. So, i.e., that for any site, you're going to put in a permanent structure or even temporary structure. You need to appreciate what level of corrosion or aggressiveness going to be. So that's part of the design requirement in there. So in terms of how you stopped like overturning of retaining structure, so for instance, take a gravity retaining wall. So the base width to compared to the height, a rule of thumb, you need to about 0.6 times your height. You say that your block will be stable. Otherwise, potentially the soil pressure or any other induced load can push you over. But certainly depends on your application. But similarly to any other type of wall, if you do like deep excavations, I think you need to have a multiple other props or ground anchors to tie them back. And the case I presented is that's why the base width got to be about 50 meters. So that again, the magic number is around 0.6. To ensure that your structure is not going to overturn, i.e., too much later diffraction at the top.
Thanks, Jim. We've had a fabulous question come in from Scott, and this one is directed to you. It says, Dr. Jim. He says, for Dr. Jim, in corrosive marine environments, does synthetic fibre, reinforced concrete come into consideration in other countries? AS3600 excludes fibres apart from basic crack control.
Yeah, that's a very good question, and I'm also in a tunneling space doing some work there as well. So yeah, yes, that's correct. But the Port Botany expansion project was more than 10 years ago. Certainly, we could not use the fibers and so on. But for more recent tunneling projects are involved. I mean, certainly the fibers actually has been applied and used for many projects now. Say in New South Wales and in other parts of the country.
Yeah, Amanda, I was going to add that could be a further answer to the innovation question that we got. That is, fibre reinforced concrete is being pushed. It's slow in the uptake here, apart from in the tunnel space, as Jim mentioned. But I think there's mileage in it. I think people we need to work at it, and we'll get it across the line for smaller walls and for different applications.
Thank you. Just touching on maintenance, we've had question coming from Rod. Direct it to either of you. How is maintenance, and who's usually responsible for the maintenance of structures? Just in retaining wall structures, just a quick summary.
Well,
Kim, sorry.
Yep. Sorry. I think it is often overlooked in the delivery of a retaining wall. So I'd encourage people to put it on the drawing, put it in your notes, put it in a report. For 100-year infrastructure projects, we certainly have to make it very clear on maintenance activities and who is doing what, and that has pre-approval. So for smaller projects, definitely it's worth talking about and what the designer expects happens to that wall after it gets built.
Thanks, Kim. And I suppose we've had a few questions around design life, which obviously are very large themes around sustainability, etc. Jim, do you want to just sort of finish up with your thoughts of maintenance, design and maintenance with regard to the life of the structure?
Yeah, I think this is actually a very important part of it. And, you know, while the question was raised, I'm reflecting actually, you know, the jobs sort of, you know, are involved. That there is a bit of a trend that, especially in certain part of it, the design requirements say, well, you know, I just want to have a maintenance-free retaining wall, for example. So this is what getting interesting. For example, if we put a drainage behind the retaining wall, we're going to lower the water table and so on. But then if you design a 6-meter retaining wall, for example, if you're going to design, say, not do no maintenance and the potential water pressure can build up behind your wall, well, you have to design the full water pressure, for example. So actually it's a balanced sort of decision. You need to talk to your client, you know, what is the expectation, right? Because so many stakeholders sort of show interest in different walls. And I recall that there was one job involving northern New South Wales. Actually, it's being constructed as we speak. The one of the maintenance stakeholders said, "Can you design something, a retaining wall? I just don't want to have any maintenance because my maintenance budget is only X dollars, you know. Otherwise, I got to come back, you see, got to fix it." Okay, well, I mean, from a design point of view, that we can do it actually with probably no maintenance. Probably is very difficult word for engineer to say. But for instance, you know, even you design concrete, but you can't say I'll never come back and have a look at what's going on. Because still getting part of it. But in terms of drainage, if you bury the drainage, say retaining wall 6 meters, you can't get access to it. Well, you can't inspect it. But if you'll be prepared to inspect it and flash out, for example, in Hong Kong, lots of retaining wall, they have a very large scheme. You go back in 30 years, 5 years, 10 years, and you check every single whip hole or drainage holes to make sure that you're not going to allow the water table build up. Otherwise, you're going to fail or move too much or even overtopping. So I think this is very kind of big topic. You know, I think overall as an engineer, we just need to appreciate what the client wants and put all these factors on the table so that a sensible decision, I suppose, can be made.
Thank you, Jim. And it seems we have run out of time. I just want to thank, we've had so many questions coming through, and we really appreciate that, you know, your levels of engagement. Hope you've enjoyed this session. Please join me once again in thanking Kim Guttridge and Dr. Jim Yang for giving up their time and sharing insights tonight. As always, we'd appreciate your feedback on the session today. So to help us improve and plan future sessions, could you please complete a short feedback form, which is linked in the description box below. Always, once again, I'd like to thank our long-standing industry partner, Austral Precast, for making today's webinar possible. Thanks again for joining us, and we hope to see you at our next webinar. Good evening.